All right, so it's Saturday. Finally, the frequency measurement test for November actually happened, and I was able to participate, get some results. I'm going to share what happened. So basically, the frequency measurement test, ARLL, has a contest or what have you, where, as it's shown here, on 40 meters and 80 meters on two stations, they broadcast a tone, and the goal is to measure that tone as accurately as possible, report your results. And one of the things I talked about this before was Doppler, the effect of Doppler. And actually, they have a nice little diagram here where they show, spectrograph of over time of one of the reference stations, and you see that during the day it's nice and solid, and at night it varies by, and of course I can't see on this picture, but it looks like it varies by a few hertz, randomly, and this is the effect of the atmosphere moving as the ionization layer moving as the sun no longer is shining on it. So that's a problem with determining the frequency, because here you have a nice solid line, and here it's varying by, it looks like, again, a few hertz. And the way that works is, as it shows here, this is at 6:30 our time. At 6:30 on a station, they call up, and so there'll be Morse code pattern that's saying something, and I did not have the audio on to actually hear what they were saying. 3 minutes later, they do a key down, which means that they transmit just the tone. And then after a minute, they do the key up, which means it's over. And then 15 minutes later, the other station does it. Another 15 minutes later, does it on 80 meters. And then the last station on 80 meters does the test. Before I did the test, and this is a printout of what my radio looks like, I tested the process on WWVB at 5 megahertz, and just wanted to make sure my method was sound. And so we can see here is my reference GPS oscillator. That's its signal, and it has a bunch of side bands from it, because it's not outputting a pure sine wave. It's from the frequency synthesizer. It's a square wave, what have you. And then this signal is the WWVB at 5 megahertz, and I'll go through what the measurement process is. But basically, what you do is there's some target, it's called X, and what I do is I set the radio 500 hertz below X. So that means that X will appear in sort of the sweet spot of the radio, and then I set my GPS 200 hertz above what I think the target is going to be. And so that's what you see here. The radio was tuned to 4.999500, which means that at 500 hertz, offset from that is where the reference is, and I'm at 700. And so then I run it through a program called FLDigi, and FLDigi, you can specify, well, actually here is, I'm tuned to the frequency, and what you see here is a graph of the spectrum of the audio. So then this has been demodulated down by 5 megahertz, and so I have just the offsets here, and so I have shown in red the unknown, and it's just a little bit above 500 because the radio has an offset, and my reference is sitting here at 700, and it's offset just a little bit because that's the offset of the radio. And this is how I can remove the uncertainty of the radio from all these measurements. And then you put a little window over each of these, the red and the green, and then it focuses on looking at the signal and finding the center point of the signal over time. And it takes a sample every half second, and that's put into a spreadsheet, which I've shown before. And then you can, from what you say is the anticipated value, it will measure offsets from whatever you put in here. And there's an issue with the software because clearly I'm at 5 megahertz, but this frequency thing, which it does all the math based on, I could not change that. And so you see, even though it says 5 megahertz in the tuner, it's referencing it off of this 14 megahertz thing, which I could not change, which sort of screws up my spreadsheet and makes me worry about my results, but okay, issues. So what you see is in the green, this is my GPS oscillator output, and there's, you know, about, what is that, plus or minus 0.1 hertz worth of noise. That can be averaged out. And then we see here is, in red, is the reference. And there's noise in the reference, and there's kind of this wandering offset, and that's the Doppler effect. And here, when I brought this down, that was when I adjusted what the expected value was. And then this was set to be, you know, 700. This one was set to be 500, and so then it actually did the measurements and plotted them correctly. So you can see that I was a little bit faster than the reference, and I was a little bit slower, and this is, again, the Doppler effect. And then we had this weird plus-minus thing that happens, and that's the radio adjusting. So, you know, the test happened, and I did a graph of the various offsets. This is the first one, and you can see this is over time. This is the sample number. And so in this area here, they're doing the warm-up thing where they're sending the Morse code, and then the test happens, and the test happens here, and that's why it's been shifted, because it's going to the actual frequency they're testing at. And then afterwards, they say something like, you know, hey, great test, or whatever. And that test lasts again a minute. And so if you look here, you know, this is the area where the test is. So 40 meters look good. You know, the deviation was, you know, plus or minus 0.3 hertz of the signal coming over. So, you know, the noise factor, that was pretty good. And then, these are all out of order. Then on the other 40 meters, I had a radio, this is zoomed in, I had a radio issue. And the radio rebooted, and it came up just the last part of the test. So here's where the actual test happened, and this is the radio where the software sort of stabilizing. The test happened in here. Then again, this is the message that occurred at the end. And of course, you have these noise spikes. That's again related to the radio. The 80 meter went well. And I think that the test happened in here, and so their introductory thing was near the same frequency, but the test happened in this zone. And then the last station on 80 meters was a complete disaster. And so this is where the test is happening. There's just tons and tons of noise, and that's maybe to be expected. And so I sort of didn't like the results I got on the last station compared to how, you know, clean. I mean, this is plus and minus a few hertz versus you know, the first station where it was, you know, plus and minus, you know, 0.1 hertz. But that's what you expect, you know, when you're dealing with radio. So then the spreadsheet that you get, here's the spreadsheet, and I've probably shown this before. It shows you the time, and so here, you know, it's 2:31, that's 6:30, so this is still in the warm-up period. It says what the transceiver's VCO was, and so the test was nominally at 7064 megahertz, so I was 500 down from that. And it recorded, this is what you can set as your expected frequency, and it gives you an error term. And so I'm, you know, 700 up. The unknown I was looking at was 500 up, and here's where I sort of gave up on setting things, because this really should be 500 and 700. But it doesn't matter because I'm doing the difference between those two anyway. And it gives you, so that in my spreadsheet, I subtract what it measures as the reference and what it measures as the unknown, these estimates, and I subtract those. And then here is sort of, the offset. But I subtract these, and this is basically what the frequency is of the unknown relative to the reference. So if I'm at 700, this means that the reference is a little bit over 500. And so what I did is, it's not shown here, but I pick the area where the test is actually happening. I average all those values, and that's what this delta is. I enter in what the error is of the GPS disciplined oscillator, because I have that count. So in this test, it would slip one cycle every 77 seconds. This is the nominal GPS frequency. I calculated what the actual frequency was based upon the slip. So, if it slips once every 77 seconds, that means that it's off by 1 over 77 cycles per 10 million. And so that's why you effectively add 0.1, you add 100th. Of course, you add less than 100th because it's a lower frequency, but that kind of makes sense. And then I subtract, or I add the delta to what the GPS is doing to get what the actual oscillator for the test was doing. And this is the math again. So like I showed in the diagram of in the diagram of FL Digi, my tune. So my tune point is at 0. The unknown shows up at 500. The reference shows up at 700. I calculate the average of the frequency between those. These both include the radio offset, but the unknown is the reference minus the delta F, and when you subtract that out, the radio offset goes away. So then the reference that you actually use is the setting of the GPS times the GPS error, and I know that the setting is what I set it to times the error factor. So here the error is 1 plus 1 over whatever the count is times 10 million. And you can think about the error. If, in that example, in 77 seconds, I got one error, that means out of 770 million pulses, I had one extra. So that's, 770 million plus 1. And I should have gotten 770 million. So you divide that out and you get the error term. And then when you cancel, that turns into 1. That's 1 over C times 10 megahertz. That's where you get that conversion factor. And then so for each station, I took the expected value, what the offset was, and I put that into the spreadsheet, and I calculated what the actual frequencies are, and then this is what gets submitted for the contest. And so I feel good about the first 40. The second 40, it's supposed to be within 10 hertz of the call-up frequency. And so here, this was 1064, and so it was, sorry, it's at 0. So there, it's +2. The second one, it was at 850, and I saw it in that diagram. I saw it on the histogram, and they would change it if there's interference. And people talked about there was interference at the chosen frequency, but I was thrown off by the radio reboot error and the software, and I'm not sure if I actually set the radio correctly, or I'm second guessing myself all over the place. On the 80 meter, again, 3 over, and here was 53 over, and I think that those are legit also because I checked what I was doing. I wrote down what I set the radio, what the radio was nominally tuned to, what the offset on the GPS DO was, but I would have felt better if I actually like taken a photo of it, not just, I'm sure I wrote it down correctly, but I don't remember writing it down correctly, or I'm sure I set the GPS, oscillator correctly for my, reference frequency. I'm sure I did that, but I don't quite remember looking at it and seeing that it's correct. So we'll know after I submit the results. But again, what disturbs me is this one was so much higher. And it surprised me, and at the time I imagine I checked just to verify that everything was correct, but I hope it is. And I do remember when I tuned the oscillator, I just changed that digit, so it's not like anyway, we'll see what the results are. So I expect the first one to be good, I expect the second one to be good, hopefully, and then the last one, it's going to be a miracle if it's within a hertz. And the second, the first 80, I feel good about it, and there's Doppler involved here. So my expectation is, within a hertz on the first three, within 5 hertz on the second one, and hopefully, minus the Doppler, 0.1 hertz. I'm hoping. And so there's going to be one more video where I talk about the results. That should be next week whenever they come out. So it's been fun. This is the thing that I built the radio for. There's another chance in April, and I'll be more in the mindset of like, take photos of all the screens just to verify, and I'll figure out the software glitch that's happening on the setting on the FL Digi program. Anyway, I'll update in a week. Thanks for watching. All right, bye.